Good day and welcome to part one of our discussion on exponential growth and decay. And I view the purpose of this section as being somewhat twofold. The first part is to see an application of these exponential functions along with some calculus that we've been discussing recently. But it also does a very nice job of introducing us to something called a differential equation. This will serve the purpose of kind of foreshadowing a bit of what you will see in the differential equations course that you may go on to take after you complete Calculus 3. So the goal is really to study quantities that grow or decay exponentially. And this is something you may have been hearing quite a bit about recently in the news, especially with that exponential growth of, say, the spread of some virus. What we would like to do is kind of get a mathematical way of representing that growth. And the following statement gives us a mathematical description. If y of t represents a quantity that grows or decays at a rate proportional to itself. And let's go ahead and see if we can express this a bit more symbolically. That is, can we put this statement into equation form? So let's make an observation. We have this function or quantity y of t, and we're told something about its rate of growth or decay. And recall, from a calculus perspective, growth or decay of a quantity is represented by its derivative. So if we had the expression dy dt, that would be referencing the rate of growth or decay of that quantity represented by the function y. Furthermore, what we are told is that it grows or decays at a rate proportional to itself. And I'd like you to pause the video for a moment and try to think back from previous courses or experiences that you've had. What does it mean for two quantities to be proportional to each other? And the typical kind of response I will get from an engineering student is usually we say A is proportional to a quantity B if and only if they have a common ratio. That is, when you divide them by each other, you always just get back a constant. For our use here, it's maybe a bit more convenient to note that two quantities are proportional if they are a constant multiple of each other. So in terms of the given statement, y of t grows at a rate proportional to itself. So what we're being told is that dy dt, the rate of growth, is proportional to y of t. That is to say, it is a constant multiple times y, where k is a constant, which we refer to as the constant of proportionality. In fact, as might seem familiar from past experience, when k is positive, this is going to correspond to growth. When k is negative, this equation will correspond to decay. And the question I have for you is, can you think of any function y that would satisfy this above equation? That is a function such that when you differentiate it, you simply get back a constant multiple of itself. Hint, it's a function we've recently investigated. And I'm going to go ahead and just write this down as a guess, and then we'll check and see that it works. So my guess would be e to the k t, because we've seen by the chain rule when we differentiate e to the kt, you get that constant k just falling out front. But we could even add another quantity in here and say that it's perfectly fine to have any constant we would like out front. So let's go ahead and double check that when we substitute in ce to the kt for the y in that above equation, what's on the left-hand side ends up being what's on the right-hand side. So dy dt would be the derivative of ce to the kt. So note, c is a constant that pulls out front. By the chain rule, the derivative of e to the kt is ke to the kt, which the order we multiply quantities, like say c and k, does not matter. We can write this as k times ce to the kt, where ce to the kt is simply our y. So I'm going to say check. We've just verified using our new calculus formulas that ce to the kt is a solution of this equation. And if you continue your mathematical journey through differential equations, it turns out that this is an equation that you will be able to quickly and easily solve with no issues whatsoever when you get to differential equations. And the only solution to this differential equation dy dt equals k of y is going to be the following function. Y of t equals y of 0 e to the kt, where y of 0 is playing the role of this constant, and what it's also kind of doing for us is nailing down an initial population or some initial piece of data depending upon what we are trying to model. So let's see the typical question that we would get asked. A bacteria culture initially contains 100 cells and grows at a rate proportional to its size. And note the key language here, grows at a rate proportional to its size. That phrase is precisely what we started with earlier. After an hour, the population has increased to 420 cells. What we would like to do to get started is find a formula representing the population at any time t. And from the information in the problem, we are told that dp dt, the rate of growth, is proportional to the size of the population. So the key phrase we've underlined allows us to get our start to solve this problem. Note that we do also have some initial data in the problem. We start off initially, or at time 0, with 100. After an hour, so I'll say p of 1, we have 420. So we know the solution to this equation. It will be p of 0 e to the kt. And we even know precisely what p of 0 is. And this leaves us in a very typical position. We've written down the solution, but it's up to some kind of constant of proportionality that we need to determine. That is why we will always require some second piece of data so that we can solve for k. So if we use p of 1 equals 420, we have that 420 is the population after 1 hour, which is 100 e to the k times 1. To isolate k, we need to use properties of exponentials and natural logs. Divide both sides by 100, and then take natural logs. So natural log of 4.2 is the natural log of e to the k, which is k. So the formula we are looking for representing the population at any given time is 100 e to the kt. So that would be the natural log of 4.2 times t. And leaving it in this current form gives us a very nice representation of this function. I will, just for fun, note that if you wanted to, you could certainly take this a step further. You could go ahead and take that t, if you want it, and make it an exponent inside the natural log. So if you did this, and you don't have to, you would have 100 e to the natural log of 4.2 to the t. The e and the natural log cancel each other. So another representation for this population would be 100 times the quantity 4.2 raised to the power t. Once we have this formula representing the population at any given time, then it also becomes reasonable to ask questions about the population. So for example, when will the population be 10,000? So what value of t satisfies this equation? And this is a very familiar type of problem from your pre-calculus experience. So I'm going to suggest pause the video, give yourself 3 or 4 minutes, solve for t. Hopefully you've done that. My first step would be to divide both sides by 100. And then if we'd like to isolate this t, we need to get it out of the exponential. And how we're going to get it out of that exponential is by taking natural logs of both sides. So natural log of the remaining 100 on the left is the natural log of e to the natural log of 4.2t. The natural log of the exponential cancels, and we have the natural log of 100 is the natural log of 4.2 times t. And if we isolate t, we have the desired time. Natural log of 100 divided by the natural log of 4.2. Which completes our discussion or introduction into exponential growth and decay. In our next video, we will investigate a specific scenario referred to as Newton's law of cooling. So stay tuned. Take care.